it up here, and I'll keep it up there just in case. So we have the position vector. Let me see if I Is that all right?
Yeah.
Okay. All right. So that's I'm gonna call it R with an arrow, and so the derivative of that is the velocity vector. Which is the derivative, which is prime, and that can also be like that, okay? But don't confuse that with v without the arrow, which is just the speed, no direction. So, which is speed. Okay. And then the acceleration would be r double prime or that, and that has its own components, which we'll go into later. Let me start off with defining the curve C, just any kind of curve, and that will have the curve has its positions vectors. Like each position in the curve has a r, and each r has a velocity or a tangent, which is of course the derivative of r. Wanting to dot, and if you take if you want it, that changes are on the curve. If you want it to be a unit vector, a tangent of it, you take r dot and divide it by itself by its magnitude. So we're just normalizing it. So it's the tangent, which is it's the same magnitude all around. So t. Only thing that changes is the direction. Same magnitude. T is r, call it that, divided by the magnitude of, is that legible? Yeah. So, and then of course the r, is equal to the F component plus the G squared plus H. This is the I, this is the J, this is the K of the position vector. Okay. This is basically much this definition we did last time. So that's a tangent vector. Okay. Okay. Unit vector.
Clarification: the F and G in that equation are there to be prime.
Oh yeah, that's right.
And just notation: the tangent at the top is r prime. You wrote it, but it's kind of covered up by the arrow.
Yeah, I didn't. So
Just want to make sure.
So it's very basic. We're just normalizing the r prime, and which goes around that. And if we want to find the curvature, which is the tangent vector changing as the curve goes on, which is curvature we'll call k equals the magnitude of the tangent vector changing as we go along the curve. We'll call this S. This is the XS direction. We want to put it in the parameter t, so we can use the chain rule. Do the chain rule to t. So we want to get it instead of ds, which is along the curve, we want to get it into dt, which is put it in the t parameter. So So ds, what we have, and then we use this, and then that'll give us, that's the equation. We can rearrange this, just simple rearranging it. dt s, which is again k, equals dt ds divided by ds dt, and then of course this is that's what we defined earlier, and then we have this defined earlier as well, which is the position vector. Okay, so that's so that's one definition of K, of the curvature of that curve. So we can just do a quick example of curvature. Yeah, I hate when the teacher goes back and refines something. I got to erase in my notes, so I'm sorry. So if we do an example, this is going to be find curvature of circle in two-dimensional space. So we're going to define a circle, and its radius is going to be rho. Okay, and the position vector for this circle, or general circle, without any coefficients. So position vector is rho radius cosine of t I, and then plus rho sine of t j. Okay. First thing we do, we're trying to get the curvature. So first thing we want to do is find the t prime, and then, well, first find the easiest one. Just take the derivative of the position vector, and then go ahead and find t prime by that definition over there. So we have r equals negative rho sine t I plus cosine of t j, and then take the magnitude, so we have that equals this component squared sine of t plus this component cosine of t, and then you guys remember this sine squared t plus so this is the identity. Sine squared plus cosine squared is 1, and then you take the coefficient, that should be the coefficient. So here you get